For this lecture, we're going to talk about section 4.5, linear approximation and Newton's method. Linear approximation helps us give an estimate of a function on a very small scale, very small interval of x. And Newton's method is a method of finding zeros when it's not something that you can factor easily or something that you can find the zeros are easily. Now, these are both things that are getting to be out of date because of the calculator usage, but you do need to be able to recognize these things. Now, if you have a function, say we have one that looks like this. If we look on a very small interval here, we can approximate the function by that tangent line that goes through this point here. And that's called a linear approximation. So what we are looking at is the equation of this line, that's really poorly drawn here, sorry, that will help us find the tangent line. So if we have, let's call this point, I can't draw a straight line at all today. Let's call this point A, the x value. So if the x value is A, that means the y value is, that's right, f of A. All right, so at this point, A comma f of A, we have this tangent line, which means the slope is the derivative at that point. Because the slope of that line, remember the slope of the tangent is the derivative at that point. So we end up, for our y equals mx plus b, if we plug it all in, we have f at a equals f prime at a times a plus our b. So our b is f at a minus f prime at a times a. So if we want to plug this in to our equation here, we have y equals f prime at a times x plus f at a minus f prime at a times a. So we took our b and plugged it in here, and took our m and plugged it in. So now we can simplify, and we have y equals f prime at a times x minus a plus f at a. And this is our linear approximation. So if we're looking at just this very small area around a, we can approximate our function by this line, and it is called our linear approximation, and we label it L of x is f prime at a times x minus a plus f at a. So this is our linearization formula. So if they give you a function and they want you to find the linearization of this function, for example, if we want to find, say we have the function f of x equals x squared, and we want to look at the point 1, 1, then our linear approximation at that point is, well, the derivative is 2x, so f prime at 1 is 2. So we've got the derivative times x minus the x value plus the function value at that x value. So this is a, and this is our f of a. So we simplify this out. So if we look at this function f at x squared, which you know looks like this, if we look at the point 1, 1 here, we can approximate what the function looks like by this line 2x minus 1. So here we cross at -1, go up 2 and over 1. So that's all linearization is. Now Newton's method is to find zeros. So the first thing you do is you guess and an approximation for x, for your x value. That gives you the function value at 0. So you guess right where it's crossing the line. So you get a close one. Then you're going to do several iterations. Okay, so you look at each x guess is the guess before it minus the function value at that original guess over the function's derivative at that original guess. So this is kind of the method that your calculator uses as its program to find it. And we're not going to really do very many of these by hand because obviously we can find zeros on our calculator really easily. So we will keep looking at that. So let's just try one example and see how this works. Okay, so here's our function, and our derivative is, of course, 4x cubed plus 1. So where do we want to start? Well, you can look at your graph and pick a starting point if you want, and I'm going to choose my x1 to be 1. Now, are you going to all choose the same x1? No, not necessarily, but should you all end up in the same place? Yes, it just may take you longer to get there. So x2 equals 1 minus the function value at 1 over the derivative at 1, which is 1 minus -1/5, which equals 6/5. So then x3 equals 6/5 minus f at 6/5 over f prime at 6/5, and you can calculate that out and you get 1.16549196. Now, it's important that you keep all your decimals in this. You can use your calculator and set up an actual function where you're using f of the answer. You set it up and you put your y1 is the function and y2 is the derivative, and then you put you hit 1, enter, and that'll be so that it's your answer, and then you can, the next function, you put answer minus f at the or y1 at the answer over y2 at the answer, and hit enter, and then you can just keep hitting enter until you get down, and you'll get x4 is 1.164037, and then x5 is 1.16403514, and then you'll find that you keep getting this one over and over again, which means that this is your 0. As I said, is this practical? Not really anymore. There's not really any use for it anymore because then your calculator will do it for you. But you do need to know what Newton's method is and have some idea of how to deal with that. There's one other thing that this section covers that we need to look at. This is differentials. Now, we'll use these a lot when we're doing rates of change, and as we get into integration, it'll be important. So what we have is we've looked at another way of writing our derivative is dy dx. Well, this is a differential, and you can actually split it up, where you have dy equals f prime at x times dx. So let's look a little bit at this There's a picture on page 225 in your book that will help you look at this, and it has to deal with the linear approximations and how different the linear approximation is from the function. So you need to read through that and look over that section to make sure you understand what a differential is and how to deal with that. Now, the main thing we're going to use it for is to find rates of change. And so I just want to do an example for that and let you read this section for all the deriving stuff. So if I give you an example where I want you to write a formula showing the change in volume of a sphere when the radius changes from A to A plus dr. So we're doing this slight little bit of change. Remember, the d is actually the lowercase delta. So we talked about rate of changes as deltas, and then the little tiny changes as the lowercase delta, the d. So how would you do that? Well, the volume formula for a sphere, which I hope you remember, is 4/3 pi r cubed. So the derivative is 4 pi r squared. And because of the way they want us to do it, we need this dr in here. So we need to rewrite this as dv dr, because we're taking the we're changing the volume with relation to the radius. The radius is changing, which is changing the volume. So if we want to just know the change in volume, then it equals 4 pi r squared times whatever the change in the radius is. That's really all there is to it for differentials. The biggest thing is you need to go, instead of writing your derivative with the primes, you've got to write it this way with the differentials, and then you'll have to split them. This means the change in volume, this means the change in radius. Okay, so you're looking for those words change and what things are changing. Make sure you've read this whole section. I hope you're reading the sections and watching the videos both, because you'll need both to be able to get a full picture of everything. Make sure that you've taken some notes, maybe tried out some of those example problems in the book on your own so that you are sure you've got it.